Today, we rely on digital computers, high-pressure hydraulics, and industrial steel to build our world. We operate under the assumption that massive construction requires this specific kind of mechanical leverage. Yet thousands of years before the first crane was ever drafted, humans erected structurally perfect monuments that dwarf our modern expectations. They achieved this without a single internal combustion engine. This story is grounded in the reality of extreme physics and complex logistics. We are looking at the tangible results of a sophisticated understanding of engineering that allowed ancient builders to move mountains. These ruins serve as the surviving technical records of extreme problem-solving. They show us how human civilizations functioned when their only resources were stone, wood, and collective willpower. The first hurdle was extreme scale. The Great Wall of China spans 21,000 kilometers, a distance that required builders to maintain a consistent structural standard across deserts, forests, and jagged peaks. To move millions of stones up these inclines, the Qin and Ming dynasties established a rigid chain of supply. Laborers functioned like gears in a massive machine, passing materials hand to hand in a coordinated effort that lasted for centuries. This relentless pace came with a heavy cost. Thousands of workers died from exhaustion and exposure, with their remains often interred within the very foundations they were building. This same reliance on coordinated movement appears in the 20th century construction of Christ the Redeemer. In the 1920s, engineers managed the assembly of this 98-foot statue on a sheer mountain peak. Every piece of stone was transported by a small cog railway and hoisted by hand-operated pulleys, a process of calculated risk performed during heavy storms and lightning strikes. When the physical requirements of a project exceed the capacity of a single human, the only solution is a sophisticated division of labor and a strictly managed timeline. Beyond scale, ancient engineers had to account for the environment itself. Machu Picchu sits 8,000 feet up in the Andes, perched directly on a major earthquake zone. The Inca used ashlar masonry to counter seismic activity. Each stone was shaped to fit its neighbor with such precision that the friction alone holds the walls together without any mortar or cement. These unique geometric angles allow the stones to shift and vibrate during a tremor. Instead of cracking, the blocks move with the earth and then settle back into their original positions once the shaking stops. While the Inca focused on stability in the mountains, the Nabateans in Jordan had to solve the problem of dehydration in the desert. They transformed the arid canyon of Petra into an oasis using a hidden network of aqueducts and clay pipes. This system captured every drop of seasonal rainfall and funneled it into massive underground cisterns, providing a reliable water source for 30,000 people. These builders succeeded because they treated environmental hazards as engineering variables, designing systems that utilized the very forces that threatened to destroy them. Some monuments functioned as large-scale scientific instruments. Chichen Itza is a mathematical model of the Mayan calendar, designed to align perfectly with the movements of the sun. The pyramid's orientation creates a shadow serpent that descends the stairs during the equinox, while the interior chambers are shaped to reflect sound waves. A hand clap at the base triggers a specific frequency, creating an echo that mimics the call of the Quetzal bird. In Rome, the Colosseum applied these principles of math and physics to manage crowd dynamics and theatrical production on a massive scale. This is the Hypogeum, a subterranean staging area located beneath the arena floor. It housed a complex system of tunnels and elevators designed to move heavy loads vertically. Using 28 different mechanical lifts powered by winches, Romans could surface wild animals and scenery simultaneously. This allowed for near-instant set changes, keeping the mechanics hidden from the audience above. This focus on visual perfection is also evident in the construction of the Taj Mahal. The main structure is a study in symmetry, but its most impressive feature is the use of light. The white marble was selected for its high translucent quality, allowing it to absorb and reflect the changing angles of the sun and moon. These examples show that the height of engineering is reached when the underlying mathematics are used to create a seamless visual or acoustic experience. We often struggle to explain how ancient civilizations achieved such precision without modern tools. This gap in our understanding frequently leads to theories about outside intervention or lost technology. However, the physical evidence points to a much more practical reality. These structures are the results of highly organized labor, sophisticated geometry, and a deep understanding of the local geology. The Seven Wonders stand as proof that our modern tools have changed, but our fundamental capacity to build has remained consistent for thousands of years. If you had the opportunity to inspect the craftsmanship of just one of these monuments, which would it be? Share your choice in the comments and subscribe for more technical looks at history's greatest structures.